Hello. In this video, we're going to introduce the notion of a continuous random variable. Our learning outcomes are thus as follows. By the end of this video, you should be able to explain what we mean by the term probability density function. We have seen this material before, but in this instance we're going to go through it again because in the previous video we were focused on the probability mass function and not the probability density function. This is because when we were looking at the previous video, we were studying discrete random variables. Now, however, we are finally in a position to look at continuous random variables. Let's briefly review the most important of the probability functions that have been introduced thus far. In the video on non-classical probability, we introduced the cumulative probability distribution function and defined it as follows. If each event S in the sample space omega has a value x of s taken from the set of real numbers script r, then there exists a cumulative probability distribution function f underscore capital X of small x that maps each subset of omega that can be formed using this particular piece of set builder notation to a number from the set of real numbers between 0 and 1. This function has the following three properties. In the limit as x tends to minus infinity, the function is equal to 0. In the limit as x tends to plus infinity, the function is equal to 1. And in addition, the function is right continuous. After having introduced this definition in the previous video, we then worked out the cumulative probability distribution function for tossing a fair coin, which I'm not going to go through again, as this should now be familiar to you. In parallel to our discussion of the cumulative probability distribution function, we've also discussed the probability mass function. The probability mass function was introduced when we discussed our game of blind man bluff and ascribed a probability to picking each of the various players. We write the probability mass function for the random variable capital X using the symbol small f underscore capital X of small x. Furthermore, the probability mass function is equal to the probability that the random variable capital X is equal to small x. For the experiment shown here, this random variable could be equal to one of the 6 different values, each of which correspond to picking one of the mutually exclusive outcomes that you could get by doing the experiment, i.e. picking Stephen, Conrad, Michael, Carlos, Maeve, or Dawn. Let's now discuss how one calculates the cumulative probability distribution function from the probability mass function. In doing so, we will play a slightly simpler version of Blind Man Bluff with only 3 players, 3 mutually exclusive outcomes. The fact that we have 3 outcomes suggests that our random variable can take only one of 3 different values, and we will use the numbers 1, Stephen, 2, Conrad, and 3, Michael to denote these 3 outcomes. Notice also that the probability mass for x equals 1, we pick Stephen, is equal to P1. The probability mass for x equals 2, we pick Conrad, is P2. And the probability mass for x equals 3, we pick Michael, is P3. Let's now draw our cumulative probability distribution function. Remember, we construct this function by building a subset of our sample space. The outcome S is a member of this subset if it is a member of the sample space omega, and if some function that takes the outcome as its argument and outputs a number from the set of real numbers is less than or equal to small x. No outcomes of our experiment give a value of small x that is less than 1, and thus for all values of x less than 1, our cumulative probability distribution function is 0. When we get to x equals 1, there is then a discontinuous change in the cumulative probability distribution function. For x equals 1, Stephen is a member of the subset, the probability that we pick an outcome with x less than or equal to 1 is thus P1, the probability that we pick Stephen. Stephen remains the only member of the subset until x reaches 2. For x equals 2, both Stephen and Conrad are members of the subset. Furthermore, picking Stephen and picking Conrad are 2 mutually exclusive outcomes from this experiment. We can thus calculate the probability that capital X is less than or equal to 2 by adding together the probability that you pick Stephen, P1, and the probability that you pick Conrad, P2. Between 2 and 3, the value of the cumulative probability is once again constant, as no new outcomes from the sample space enter the subset. However, all three outcomes, Stephen, Conrad, and Michael, have X values that are less than or equal to 3. And thus, at X equals 3, the cumulative probability distribution function jumps to 1, suggesting that generating a random variable less than or equal to 3 is assured. Let's now turn to a slightly different scenario. Let's suppose that the outcome from our experiment is a number between 0 and 1. There are an infinite number of numbers between 0 and 1, so we cannot construct a probability mass as we did in the previous example with a game of blind man's bluff. We can, however, draw a cumulative probability distribution function immediately instead. We know that all outcomes from our experiment are between 0 and 1. Hence, for all x less than 0, there are no outcomes of the experiment in the set formed by taking all outcomes with random variables less than x. Hence, the value of the cumulative distribution function must be 0 for all x less than 0. We can apply similar logic for values of x greater than 1. We know that the outcome from our experiment will always be between 0 and 1. Hence, for any value of x greater than 1, the cumulative probability distribution function must be 1, as all possible outcomes of the experiment will give a random variable less than x. We can then fill in the space between these using the fact that all outcomes between 0 and 1 are equally likely, as this implies that the probability of generating a value less than x will increase linearly as x is increased from 0 to 1. Putting this a different way, as you increase x, the proportion of outcomes with a random variable less than x increases linearly. Hence, if all of these outcomes are equally likely, the cumulative probability, the probability of generating a random variable that is less than or equal to small x, should also increase linearly. In the previous video on non-classical probability, we discussed the following limit, and how this must be obeyed at all the points along the probability distribution function. We visualized what this limit meant by drawing a blue circle at x, as shown here, and a green circle at x plus epsilon. And then we showed that as we decreased epsilon, the green circle moved back along the curve until it overlaid the blue circle for epsilon equals 0. In this way, we showed that the limit shown was satisfied by the cumulative probability distribution function. When discussing this limit, we also talked briefly about the limit shown here, where instead of having x plus epsilon, we had x minus epsilon. In the previous video, we showed that this limit did not hold for the cumulative probability distribution function that we obtained for tossing a fair coin. Here, though, this limit is true. Once again, we place our blue circle at x and our green circle at x minus epsilon, and show that when epsilon is decreased to 0, that the green circle overlays the blue circle. The fact that both the plus epsilon and minus epsilon limits are equal to f of the cumulative probability distribution function evaluated at x is important, as it implies that our cumulative probability distribution function is continuous and thus differentiable. When neither of these limits, or only one of them hold, the function cannot be differentiated. An interesting exercise is thus to draw a graph of the derivative of the cumulative probability distribution function as a function of x. As an exercise, pause the video and see if you can draw this curve. Your curve should look something like this. For x less than 0, the cumulative probability distribution function is a horizontal line, and the gradient is thus 0. Between 0 and 1, the function increases linearly. The gradient, or derivative, is thus constant. In fact, it is equal to 1 as x changes from 0 to 1 and y changes from 0 to 1. For all x greater than 1, the curve is once again horizontal and our derivative is thus 0 once more. Now remember that integration, calculating the area under the curve, is the opposite of differentiation, finding the gradient of a tangent to the curve. We can thus take the derivative of the cumulative probability distribution function that we have just drawn and recover the original cumulative probability by finding the area underneath our horizontal line. This process is illustrated in the following movie. The area of the shaded region underneath the lower curve corresponds to the value of the blue dot shown on the upper graph. When we have a cumulative probability distribution function like the one we have just seen, which has a derivative by virtue of being continuous, we call the derivative of the cumulative probability distribution function the probability density function. This is given the symbol shown here. It is also sometimes written like this, although saying that the probability density is equal to the probability that the random variable has a particular value is not quite strictly correct, hence the inverted commas. There is good reason for writing this though. As we have just seen, we can recover the cumulative probability distribution function from the probability density function, the derivative of the cumulative probability, by taking the following integral. This looks rather similar to the way that we recover the cumulative probability function from a probability mass function, when we had a random variable that could only take on discrete integer values. This equation for doing this is shown here. If you remember, for these discrete random variables, we also had that the sum of all the elements of the probability mass function was equal to 1. We have a similar condition for the probability density. The integral of the probability density over all space is equal to 1. We thus arrive at a useful rule of thumb. When you move from a random variable that can take on discrete integer values to a random variable that can take any real number, all the summation signs that you had turn into integral signs, and probability mass functions change into probability density functions. This holds for the normalization conditions, the way that you convert from a probability mass / density to a cumulative probability, and as we will see, the way that we calculate expectation values. For now though, let me finish and summarize by reminding you of the important new probability function that we have learned about in this video, the probability density function. The probability density function is equal to the derivative of the cumulative probability distribution function. I hope you've been able to understand these concepts from the video. If not, watch it again and see if you can get them on the second go through. Thank you for your attention.